most science papers, we can find examples of null hypothesis significance testing, typically attributing statistical significance to the findings if the so-called p-value is below a certain threshold. The meaning of p-values is often misunderstood, so in this video I will give a behind-the-scenes tour of what happens to our data before we reach a conclusion about statistical significance. First, I'll give an overview of null hypothesis significance tests, then we'll work our way through an example. Finally, I'll close with some properties and misinterpretations of p-values. A null hypothesis significance test allows the scientist to compare a group of data points against a null hypothesis. If the data are an outlier with regards to the statistical model defined by the null hypothesis, the result is said to be statistically significant. For this process, the scientist needs to define two things: the null hypothesis, which defines a statistical model of the observations expected under the default assumption, and the statistical hypothesis test, a method to quantify how strong an outlier a given group of data is. When comparing data from a control group and an independent study group, a so-called two-sample test, the null hypothesis could assume that both populations follow a normal distribution with equal means and equal variances. The null hypothesis is sometimes denoted with H0. By population, we mean an infinite line of people in a similar condition as either the control group or the study group, even those who aren't even enrolled in our experiment. By sample, we mean one group of data taken from either the control population or the study population. Since an experiment involves multiple data points, we need a process to compare the study group against the null hypothesis. The statistical hypothesis test is responsible for this. Each set of observations is reduced to a single number called a test statistic. As an example, we could find the average distance from the group average. This would work, but as we'll see, the actual calculation is more involved. The process is as follows. Calculate the test statistic for an actual experiment. Generate simulations of experiments assuming the null hypothesis is true. Calculate the test statistic for each simulated experiment and order them. Measure where our observed test statistic lies compared to the simulations. Then the p-value is the ratio of hypothetical experiments that satisfy the null hypothesis with at least as extreme a test statistic as that from our observations. If the p-value is less than a predefined significance limit, typically 0.05, then we reject the null hypothesis. The result is said to be statistically significant. If the p-value is higher than the significance limit, then we cannot reject the null hypothesis. However, we cannot accept it either. This procedure can only falsify a null hypothesis. It cannot confirm or prove it under any circumstance. Let's see this work in a concrete example. Imagine an experiment to assess whether a weight loss drug is effective. You end up with 32 data points from a control group, those who received a placebo treatment, and 24 data points from the study group, those who received the tested drug. We want to compare the study group against the control group and see how incompatible our data is with the hypothesis that the two populations have the same mean. We set a significance limit of 0.05. The observed data is as follows. We recorded the weight of each participant at the end of the study in the percentage of their initial weight. We could do some eyeball statistics, plot the histograms and compare them, but that wouldn't be the height of objective analysis. If the following assumptions are true, then we can use student's two-sample t-test. First, the means of the two populations follow normal distributions. Note that it does not mean that your beliefs have a normal distribution. Rather, if you were to sample 1,000 more groups with the same sample size, those 1,000 means would follow a normal distribution. This is almost always true thanks to the central limit theorem. Second, the two populations have the same variance. In case this is not necessarily true, we can relax this with another t-test variant. And third, the data from the two populations were sampled independently. Intuitively, student's t-test answers the following question: how far away are the two groups relative to how far away they tend to be under the null hypothesis? The most likely estimate of the difference between the two groups is the difference of the sample means. This is the basis of our calculation, but we need to put this in perspective using the standard deviation of the populations. A big difference is more likely if the data in both groups are spread out rather than gathered around the group averages. How compatible is the 3.1% difference with our null hypothesis? That's the question. A figure that will come handy is the sample variance of the two groups, which is approximately the average squared distance from the group mean. Intuitively, this describes how spread out the group is. In our example, the second group's variance is slightly higher, and indeed, the second group's histogram does seem more spread out. Because we assume that the variance is equal among both populations, we can use a pooled estimate of the standard deviation using the data from both samples. This is the weighted average of the two sample variances. Instead of the variance, it is often more useful to talk about the standard deviation because that has the same units as the data itself. In this case, the percent of weight change. The standard deviation is simply the square root of the variance. All hypothesis tests need a test statistic, and for student's t-test, this is the so-called t-statistic. This is the ratio of the departure of the estimated value of a parameter from its hypothesized value to the standard error of the estimate. Now that's quite a mouthful, so let's unpack it. The estimated difference is simply the difference of sample means. The hypothesized difference is 0, the value we are testing against. The standard error is the standard deviation of a series of hypothetical experiments, just like this. Fortunately, that can easily be calculated from the estimated standard deviation. In the end, we arrive at a negative t-statistic because the study group had a lower average than the control group. The study participants lost more weight. Now that we have the observed test statistic, we simulate a gazillion hypothetical experiments that follow the modeling assumptions and the null hypothesis and the sampling intentions with the hypothesized parameter value, i.e., populations with equal means. Then we calculate the test statistic for each and calculate how many of them is more extreme than what we observed. In this case, more extreme is defined at the beginning of the analysis as lower than the actual t-test statistic because we wouldn't count as a success if a weight loss drug increased the weight. This means we are calculating a one-sided p-value. More simulations would lead to a more accurate p-value, Of 1,000 simulated experiments, approximately 116 would have a more extreme test statistic, so the p-value is 0.12. As the p-value is higher than our significance threshold, we cannot reject the null hypothesis. Although what I said was true, in practice we don't need to simulate experiments, because the distribution of t-values can be calculated directly for any sample size. We can just mark our t-statistic on the chart and calculate the area under the curve to the left of it. Lo and behold, that's the one-sided p-value of 0.116, which is very close to what we found with the simulations. Again, the p-value is the ratio of hypothetical experiments that satisfy the null hypothesis with at least as extreme a test statistic as that from our observations. For every 100 experiments where the null hypothesis is true, in 5 experiments the p-value is less than 0.05. This means that the cutoff for statistical significance, which is typically 0.05, defines the false positive rate, i.e. the ratio of experiments where we announce a statistically significant effect, where there is in fact none. However, this does not mean that 5% of all experiments are false positives. Studies on reproducibility estimate false positives much higher, but the exact figures depend on the field. The p-value is not the probability that the null hypothesis is true. Null hypothesis significance tests can't give you probability estimates. Bayesian statistics can. A high p-value does not indicate that the null hypothesis is true. Maybe the study was underpowered, the measurements too noisy, or another hypothesis would also be compatible. A low p-value does not indicate a scientifically significant result. The null hypothesis can be false even if the effect size is tiny. Parameter estimation is recommended to find alternative parameter values. The p-value does indicate how incompatible the data are with a specified statistical model, but it alone should not be the basis of a decision. Undervalued factors are the related prior evidence, the plausibility of mechanism, study design and data quality, real-world costs and benefits, novelty of finding, and other factors that vary by research domain.